Swayam Prabha. Digital India. Educated India.
Welcome to lecture 3 of week 7 of this NPTEL course on muffler acoustics. So, as informed in the end of the last class, last lecture, lecture 2, I talked about deriving the loss factors and basically the transfer matrix in the presence of mean flow for an extended inlet and outlet element, where we sort of incorporate the loss factors or the loss in the flow that is happening because of the mean flow effect. So, now towards this end, what we do is that we sort of revisit some of the muffler elements that we probably introduced in the week 3 or probably beginning of week 4. So, here we have, and let us say we have, using the previous nomenclature, we have this muffler element. Let us call this part as point 3 and the part that is right here is point 2 and this guy is 1. Okay. So, here we have this thing and there is a cavity and here we have a flow. So, this is an extended inlet element. The derivation that I am going to talk about now is sort of equally applicable to an extended outlet element. Here we have pretty much the same nomenclature, that is your, apart from the fact that the chamber was, the point in the chamber was mentioned as point 1 and here a point just at the interface of the chamber and the port, but in the port itself is mentioned as point 1. Okay. So, the thing is that we would like to develop a relation between a transfer matrix relation between the point 3 and 1 or 3 and 1, the flow is here in this direction. So, when it expands. So, what happens, we have already seen, we already know pretty well, by now it should be clear that this guy, the annular cavity, what does it do? This acts like a quarter wave resonator. It is a quarter wave resonator and it acts like a shunt element. So, this transfer matrix, whether for this one 3 to 1 or 1 to 3, for the K, I need to rub this guy, is understood here, that was pretty straightforward, P3 V3 for classical state variables. This was pretty sort of straightforward. There was 1 by Z2 1 0 and P1 V1 and Z2, say let us say this length is L, okay, is minus J Y naught K naught L. Alright. So, this one was pretty clear because P3 is equal to P1 and is also equal to P2, and velocity, mass velocity that enters here gets split into two parts, one that goes into the annular cavity and the one that propagates downstream. So, V3 is equal to V2 plus V1. So, that one was pretty clear, and we sort of eliminated some variables, that is the variables pertaining to the annular cavity 2, and found out the transfer matrix between 3 and 1. So, in case of 0 mean flow, this is what we get. We do not have any problems with it. So, whether it is an extended inlet or extended outlet element, it does not quite matter. However, when we do have flow, things would be a bit different. So, we will see how to incorporate the flow losses that happens here. So, basically let us first, although we are going to talk only in terms of qualitative discussion, because quantitative discussion would involve some flow simulations, some CFD simulations to simulate the flow field in such a cavity. But basically when because real fluid will have viscosity. So, when you have flow coming in here, so and it is sort of going out, again there will be a potential core, as we were discussing just at the beginning of this week's lecture, and there will be vortices that will be shed, and it will create some noise. Okay, it will definitely create some separation noise, but then there will also be something like a head loss, there will be loss associated with sudden expansion of the flow. So, that is going to probably aid in greater attenuation, but then the main worrisome feature is the noise that will be occurring due to the free shear layers that are formed here in the after the collapse of the potential core. So, that really is the culprit, and it is from our experimental observation that you never actually allow the flow to separate like this. You actually connect it by a perforated bridge, just like I was mentioning at the beginning of the last lecture. So, but nevertheless, for the sake of completeness of this theoretical development and what has been usually classically taught, we do consider some loss factors, what we can get. Basically, they are like they are related to head loss when the flow expands suddenly from a pipe, and that would actually, like I said, aid in the attenuation. So, let us first get that, but obviously one would never allow the flow to expand or contract suddenly. It sort of is counterproductive, but we still derive some theoretical expression that it would sort of need much more comprehensive modern experimental validation. Let us begin our derivation for this thing. So, now let us consider extended inlet element. This is your extended outlet. Okay. So, let us focus on the figure A. All right. What happens across this discontinuity? So, unlike in the case of a static medium, that is where there is zero mean flow, where the pressure is constant like I mentioned and the mass velocity gets split into two parts, here the stagnation pressure or the perturbation pressure P c decreases across an area discontinuity. So, the stagnation pressure, the perturbation pressure, the convective pressure P c, not P tilde, P c tilde, that decreases across an area discontinuity, and because as the flow passes a certain change, a part of the flow acoustic energy is converted into heat or basically losses. So, that results in an increase in entropy. So, that entropy increase only in an approximate manner can be accounted through a parameter, which is again sort of measured or experimentally determined for loss in stagnation pressure for incompressible flows. So, basically at such a point you have, let us say Ps, that is a stagnation pressure at the point 3, which is just upstream, is equal to the stagnation pressure at point 1, but you also have a loss factor half into rho naught into, let us say u1 is the velocity in the chamber. So, again continuity will apply, but we will probably come to that later in a bit. So, here we have this. So, K takes a certain form depending on whether it is a sudden expansion or a sudden contraction, or it is a reversal come expansion or a reversal come contraction based on the elements that we discussed in week 3, I believe, or towards the beginning of week 4. K is sort of known from that thing, although only approximately through classically, but here this will hold when m1 or m1 square is much less than 1, or m3 square is also much less than 1, as for highly subsonic flows. So, now if we were to expand this stagnation pressure into the pressure that plus your velocity contribution due to the velocity head. So, here we have this, because stagnation pressure is equal to the the pressure in the fluid plus your half rho u squared term, and here you have this. So, now this loss coefficient, I will probably talk about that, present a table later, but what we immediately need to do is that since we are doing acoustics, we need to do some apply some perturbation. So, this equation needs to be perturbed. So, how do we do that? How do we exactly go about perturbing it? So, basically we get, let us say we do P 3 tilde and half into rho into u 3 plus u 3 square, and this is something like this, and P 0 1 plus P 1 tilde plus half into rho into u 1 plus u 1 tilde square plus half into k. I will keep the k as it is, okay. And so we get this, all right. So, now what we need to do is that let us say this is equation 1, this guy is equation 2. So, if we subtract equation 1 from 2 and since look we have a lot of ground to cover. So, I will start avoiding the complex simplifications that is there and directly present you the summarized sort of result. So, the idea is that to subtract this entire guy from this particular thing. Okay. So, 2 minus 1, okay, we will do that, and when you do that and simplify matters, do the algebra. So, what you will get is P 3 tilde plus rho naught u 3 and u 3 tilde is equal to P 1 plus rho naught u 1 and u 1 tilde plus k times rho naught u 1 and u 1 tilde. Okay. So, we get that, and then once we simplify this thing, these guys further, we get P 3 plus M 3 y 3 V 3 is equal to P 1 plus M 1 y 1 and V 1 plus k times M y 1 into V 1. All right. Clearly, we can write these quantities in terms of the aeroacoustic state variables. So, we need to bring into knowledge or into application all our things that we are doing in the last couple of lectures. So, P C 3 is equal to P C 1 plus your K M 1 y 1, and what we will do is that we will do 1 minus M 1 square and V C 1 minus your M 1 P C 1 whole divided by y 1. So, this happens because you need to basically sort of replace some of the classical variables that we have here in terms of the aeroacoustic state variables. So, once we do that, we get this particular thing. So, all the details you can work it out, because let us go back to some of the last slide. Where did we define the relation between the classical and the aeroacoustic state variables? So, it was I guess all written somewhere here. P c is equal to P tilde plus M naught y naught V c. So, clearly this is the guy that we are using. There was yet another one which is basically your velocity was this one, okay, V tilde plus P tilde M naught y naught. So, we just need to get the proper relation using the appropriate subscript and sort of get back. So, once we do all the maths behind it, what we will do is basically put in all the relation in terms of the convective state variables and simplify the maths, and to finally end up with the following relation: 1 minus k M 1 square 1 minus M 1 square P C 1 plus your k M 1 y 1 1 minus M 1 square into V C 1. Okay. So, we get this sort of a relation. So, now like I said, for all practical purposes M 1 is approximately 0.15. So, M 1 square is much less than 1, and so it can be neglected with respect to unity or with other terms which are of first order. So, what does it really mean? It basically means that here we have quadratic terms in this equation. So, can we sort of neglect this thing, because here you have, if you neglect this guy, you still have a second order term in the numerator, which should be much sort of smaller than the unity term, because k ultimately is a loss factor. It's sort of it's small, it's less than unity. So, basically this entire term is much smaller than 1, provided that M 1 square is much less than 1. That is what we do, and then we also ignore or neglect the M 1 square in the denominator. So, what we get is basically P C 3 is equal to P C 1 plus your k times m1 y1 and Vc1. All right. So, we get this relation. So, now after this we probably would also like to note that density perturbation, we have your quantities like rho 3 tilde that is related to the acoustic pressure fluctuations by your isentropicity relation. You know the relation basically what happens between the upstream and downstream variables. So, this is always there, and at a downstream rho 1 tilde is equal to P 1 tilde minus S1 times P naught by CV by C naught square. So, what are all these quantities? These probably are these the quantities that we are looking at the first time? Well, S1 is the entropy, S1 is not the cross sectional area here, it is the entropy term in the chamber because it is an extended inlet element as we sort of see here. Now, this is what we get, P naught is the ambient pressure and CV is the specific heat at constant volume. So, these are all sort of thermodynamic relations. I probably would not go deep into this part. I would just say that well, you know, this is what we get when we have entropy term generation in the downstream. But you know, it's been fortunately it's been found out that the entropy contribution is only of the order m1 square, that is, you know, all this entire term, the one circled here, this is of the order m1 square. So, basically it does not contribute that much as this term. So, we would sort of neglect it. One is sort of referred to the previous papers by Panikkar and Munjal, published a long time back, probably in the Journal of Indian Science, published in 1981 I believe, where they did all these thermodynamic derivation and showed that these quantities are of order m1 square. So, eventually what is the purpose of all this thing is that we are going to have this kind of a thing, isentropicity relation between P3 rho 3 and P3 and rho 1 and P1. Okay. So, we will keep this handy. Now, another thing that comes to our mind while doing all this is the continuity relation. So, we have your rho naught, basically whatever mass flux goes here, it has to come out of 1. So, continuity is, I mean, it is very important. So, it has to be maintained. So, rho naught S3 into U3 is equal to rho naught into S1 into U1. Okay. Now, as usual we go about our business of doing perturbation. Rho 3 tilde S3. So, let us quickly sort of write it down. This would not take too much of time. Rho naught plus rho 1 tilde into S1 into U1 plus U1 tilde. So, this is what we get. So, again we drop the second order terms like rho 3 tilde and U3 tilde, and the first order terms cancels out, because you know again equation 1, equation 2, subtract, expand the equation 2 out completely, there will be 0th order terms or the ambient terms, first order terms and second order terms. Second order terms like rho 1 tilde into U1 tilde, that will be very small compared to the first order terms. So, ignore that, drop off that, alright, and retain only the first order terms. Subtract equation 1 from 2. So, the resultant equation would look something like this: rho naught S3 U3 tilde plus rho 3 tilde S3 U3, U3 now is the mean velocity, not your U tilde, and rho naught into S1 U1 tilde and here rho 1 S1 U1 and rho S2 U2. So, we get this. Now, what we immediately realize, this is nothing but the mass velocity V3, and rho 3 tilde is nothing but your P3 tilde by C naught square, alright. We get that kind of a thing. So, we get P3 tilde by C naught square into S3 U3 is here the is the mean flow thing, and this is nothing but V1 tilde and here this is really your P1. So, here we get P1 by C naught square S1 into U1, and perturbation or the acoustic mass velocity in the annular cavity. So, here we have this relation, again using your convective state variables. What we figure out, U3 by C naught is nothing but M03 or M3, Mach number in the the tube, and C naught by S3 is your Y. The same argument goes for this particular term and these two terms. So, basically we are in a good position to write these guys as VC3 is equal to VC1 plus V2, okay, the convective state variables. So, you see we have got these guys, okay. This one, other equation was this one, let us call this as star and let us call this as cross. So, we have got these star and cross equations. Look, what is our aim? Our aim is to first relate things between point 3 and 1. So, we have got two equations. We know K depending on the kind of discontinuity it is, whether it is an extended inlet discontinuity or extended outlet discontinuity and so on. So, here we in this equation pretty much there is no unknown here, in the sense that there is no variable for the annular cavity. We just have things in the point 3 and 1 and the loss factor, and here we have V2. Now, however, to eliminate V2 we would need one more equation. So, how do we go about doing that? So, here the momentum equation then comes in handy, and what we do is that for the extended inlet element like the one that is sort of seen here 3 and 1, we must apply certain relations, all right. So, what do? We basically put your P naught is the pressure into S3, isn't it, plus rho naught S3 U3 square, okay. So, we have got this thing plus C1 times, C1 is a constant, will be this is basically for an extended inlet outlet element, C1 is minus 1. So, here we have minus 1 and P naught into S1, here we have this, plus rho naught times S1 U1 square, we have this kind of a thing, plus your C2, you can write C2, but you can, this is probably 1. So, P naught into S2 is equal to 0. So, we have this momentum equation. Now, this minus sign here and the plus 1 that goes on here, that is only for an extended inlet element. For an extended outlet, here we will have minus. Let us first deal with an extended inlet, the figure that I had just drawn back in this slide, the figure A. For figure B, it will be minus. Anyhow, so what we will do is that we will perturb the equation as usual. We will go about doing our perturbation business. So, P1 P3 tilde into S3 plus rho naught plus rho 3, it is going to be a little tedious. So, what as we usually we do, I will skip some of the algebraic simplification, with the understanding that you guys would take it up at some stage. So, this thing will be equal to your P naught plus P1 into S1 plus rho naught plus rho 1 tilde S1 and U1 tilde square plus P naught plus P2 tilde S2 is equal to 0. So, we get that. Now, again we will subtract the star marked equation from double star equation, and one can do the algebra to dropping second order terms and first order 0th order terms anyways cancel out. So, S3 into P3 tilde plus 2 rho naught S3, and here you have your Mach number M3 and C naught here and u3 tilde plus rho 3 tilde s3 u3 square minus term here, and s1 p1 tilde plus 2 rho naught s1 u1 tilde rho 1 s1 u1 square plus s2 into p2, okay, is equal to 0. So, we get that. Again we sort of make use of the convective state variables, and with the understanding that we had in the last few equations, what we eventually get up is S3 times so we get this part we get this. Now, P2 by V2 is equal to Z2. So, what do we do now? Z2, that is the impedance seen at right at the entrance of the annular cavity, and that we know is nothing but minus jy2 into cot of k naught L2. In the annular cavity there is no mean flow. So, that is why we are getting k naught. So, after doing all these things and substituting, making use of this relation, what we get after significant algebra is that VC3. So, just let us go back just a little back, and we see that VC3 is equal to VC1 plus V2, okay, and we did all this algebra, and finally after a significant sort of simplifications, we will get S2 Z2 and S3 M3 Y3, okay, we will get that, and this is multiplied by C2 S2. So, C2 is 1 and S2 is just S2 PC1 plus S2 times Z2 minus M1 Y1, and C1 is your minus 1. So, minus S1 plus K S3 VC1. So, we get this relation, and once we put this in the convective state form, it's going to be a rather complicated thing, because now we in this, by the time we arrive at this point, we would have neglected the m square terms. Now, all these things can be further written in an approximate manner as K1 K M1 Y1, and your here you will be having S2, you will be having S2 and S2 Z2 plus S3 M3 Y3, and here you will be having S2 Z2 minus M1 Y1 and minus S1 K S3, and the denominator you are having S3 M3 Y3, and this thing will be eventually related to VC1. This is a lot of algebra. There are a few important cases or corollaries that we would like to probably note here. When this guy, we have this particular thing, okay. Now, what happens if your thing is flush mounted, if your inlet pipe is flush mounted. So, basically impedance right here, that is cot k naught L, L is 0. So, cot at 0, that is your it is tending to infinity, is not it? This guy is going to infinity, and this is tending to a very large number, and so all these terms are very small in comparison. So, basically the result will be that this guy will be 0, okay. What about the things here? Here also we have Z2 in the numerator, in the denominator and these are all finite terms. So, basically you will be having sort of 1 here, is not it? You will be having 1 here. So, that is the case of a sudden expansion. Okay. So, we are deriving the case of sudden expansion in a very simple manner using this. So, we have 1 and your k m1 y1 0 1, the relation between the convective variables across a sudden expansion incorporating the loss factor. So, this loss factor will actually what it will do for a simple expansion chamber. Incidentally, the loss factor for sudden contraction would be different from that of a sudden expansion, but whatever it is, this kind of a transmission loss you are getting for a case of a 0 mean flow. So, in case of non-zero mean flow, these troughs will be slightly lifted, based on theoretical predictions, and these peaks will be slightly lower, this attenuation domes, but these are all theoretical things. Experimentally, and pretty much the same thing will happen for this thing. So, for an extended inlet or extended outlet element, what one would typically imagine is that for a tuned thing that we are kind of thinking, the first order trough will be lifted, the second order trough will be lifted, third one will be lifted, and so on. So, these flow what it will do, it will basically lower the troughs, and these things will go up. It will basically wherever there is a trough, it will try to lift it up. So, it has a smoothing effect or a leveling effect, but typically these are all predictions without really considering the flow induced noise at the expansion, that is here, or at these points like I was mentioning. There will be vortices being shed which will be interacting with the duct and will create a lot of noise. So, all these things are sort of very classical ways of predicting losses that will be generated, but then one really has to develop newer expressions for the actual flow actual situation when you have a non-zero mean flow and the flow is allowed to expand suddenly. It will actually not be very productive, they will be counterproductive, especially when your muffler shell is very thin and it radiates noise outside, and the transmission loss of course will also come down because of this. We have some experimental proof for the recently conducted work, but the main thing, this basically brings us to the premise of why we should go for a perforated system. So, we have typically we would never allow the flow to expand so freely, I mean. So, what we do is that, so this brings us to the topic of perforated mufflers, and right now we are just going to discuss very briefly in the next couple of minutes or 5 minutes about why do we need to have perforates, what purpose does it serve, and maybe I will show you some nice photos available in the internet about some cool perforated mufflers chambers. And so, basically what you do is that you connect while we have tuned the chamber L by 2 and this is L by 4 for instance. So, we typically there will be higher order modes generated. So, at later points in the course we will hopefully do some derivation of the higher order modes without the perforates, but the idea is that higher order modes will be generated. So, you can tune this by slightly reducing the length here, the geometrical length and so on. Now, the perforated bridge length will increase. Okay. So, when it does so, I mean this gap will increase. So, basically what you need to do is that connect the inlet and outlet pipe with a perforated bridge. We will connect that, and so we do not allow the flow to sort of expand. We never allow the flow to expand, it just goes away, and it interacts with the annular cavity. It interacts with the annular cavity. Okay. The waves interact with the annular cavity and they have resonances here and resonances here, but the flow itself just goes smoothly. So, there will be a minimum pressure drop, and because there will be no free shear layers formed, there will be no vortices that are formed in the wake which would otherwise form if the perforated bridge were not there. So, the flow induced noise, the counterproductive noise will not be there. So, the flow can smoothly go away like this and leave the outlet here, but at the same time a highly perforated bridge. So, we will discuss all the parameters that are relevant to discussion of perforate, especially when you talk about impedance. One of the important parameters is sigma or the porosity, which typically sort of varies between 5% to about 30%. 30% porosity means it is basically the open area ratio. So, it basically is nothing but a pipe on the surface of which there are holes, small holes are there at some interval. There have been different manners in which perforated things are drilled. So, through these waves, through these holes, the waves are allowed to interact with the outer cavity. So, if this is 30%, then it is highly porous, it is virtually like it is acoustically transparent, but at the same time mechanically it is allowing the flow to go through. So, these holes are very small, about roughly 2 to 4 mm diameter and placed at a certain spacing. So, we see these perforated things very commonly. I show you some photographs of the perforated stuff that we did some time back. So, basically not allowing the flow to expand freely, but at the same time allowing the waves to interact with the cavity is what the perforate does, and it really kills or does not bring into picture the separation noise. And experimental evidence has it that this is much better than just allowing the flow to expand. And in real life also, no one really uses a bare extended inlet and outlet chamber. People really need to use some perforated thing, and that is why this perforated elements are studied a lot. And in all commercial vehicles, I will show you a couple of photographs, they are there. And there is another element also, perforated thing. There is something like this is here, the flow just grazes the surface, but there are other elements which something like, let me just sort of draw it quickly for you guys. So, here you can have a solid pipe and we have a overlapping element, and okay. So, the flow has to go through this, flow has to go through this. Okay. So, basically such a element is called a cross flow expansion chamber. So, here cross expansion takes place, is no longer a grazing flow, flow has to go through this. So, the perforated impedance expression sort of changes significantly. So, hopefully we should be able to do that as well. Now, let me show you some nice photographs of the interiors of how the typical perforated element looks like. So, we see these perforated tubes. So, these are something that we fabricated some time back. This is nothing but something like 2.5 or 3 mm MS steel pipes, and a number of holes were drilled at regular intervals, as you can see here, about 2 mm, 3 mm holes, and they drilled at regular intervals. This is definitely highly porous because porosity is about 28 to 30%, somewhere between that, and this is about only 12%. So, acoustical properties, the final thing that matters is transmission loss of a muffler, which is highly dependent on the porosity. So, we did some experiments some time back and figured out that this is highly porous, and this is as good as acoustically this being not there, but the presence of such a perforated thing is very crucial, because this is what eventually will happen. You see, this is the part and this connects, of course, this is a let us say there is the inlet, this is the outlet where my mouse is pointing, the flow comes in here and it is smoothly guided by the perforated pipe and leaves outside. It does not allow to expand, not allowed to freely expand. The acoustic waves nevertheless are allowed to interact with the cavity, and the cavity is not empty now. As you can see, it is surrounded by some sort of a glass wool and mineral wool and all that. So, these are nothing but dissipative materials. They completely kill or dissipate the acoustic signal. So, basically this is a completely fully perforated muffler, but it is also the annular area is filled with absorptive sort of materials. So, it is fully dissipative. So, the crucial idea is that the perforated thing acts like a guide. It does not allow the flow to expand out freely, and it interacts with the annular cavity, and then that is what happens. So, this is a straight through muffler with a least pressure drop, and the flow noise that I was talking about will not be there. And then this is yet another more complicated mufflers. Hopefully, we will be doing some plane wave analysis of this thing next week. So, basically the flow comes in here as it is shown somewhere here, inlet, and this is an outlet, but in the process it has to negotiate number of turns, like the flow is reversed here, it is an end chamber. We remember in your last assignments you dealt with propagation along this axis, and similarly along this axis, because wave propagation is here, and in the annular area it is filled with absorptive materials. So, the idea behind all this is that the flow has to essentially cross over this thing. The flow has to basically bend around, and some part of the flow kind of interacts with the material and interacts with the annular cavity, which is filled with absorbent material. But if it is not filled with absorbent material, it can still, the flow necessarily has to also go through some part in here, and there will be a number of passages through which the flow has to pass, and then it will be a cross flow expansion chamber. So, different expressions will involve. So, this photo really tells you how complicated a real time muffler can be. So, this involves multiple interactions with the annular cavity and produces the desired transmission loss. So, there is lots to be done. Obviously, with this note I would like to end this today's lecture, which is a bit large, but there is lots to be done. There is still a lot of areas not quite explored, and with so many dimensions, Perforate really adds a lot of dimension to our thing. So, especially with the number of more elements like short end chambers and dissipative materials and all that. So, not everything can be covered in this course, but only glimpses of these things probably can be given. So, tomorrow what we probably would be doing is, for the first time we will be talking about concentric perforated expansion chamber, in which only plane waves will propagate, and get some equations, and finally do some hopefully transmission loss calculations. But before that, we would also need to thoroughly have a decent idea of the different perforate impedance available in the literature. So, we will try to present that in the lecture 4 and lecture 5 of this week's lecture before moving on to the next week. So, thanks a lot, stay tuned, I will see you in lecture 4.